Hi everyone. Today we are going to be discussing the second way you can multiply two vectors, known as the cross product. So unlike the dot product, which gave a scalar value, or just a number, the cross product will actually output a vector. Hence, it's also known as the vector product of two vectors. So the big idea with the cross product is that the cross product will generate a vector that is perpendicular to both A and B. In other words, we are going to be working a lot in three-dimensional space. So let's go ahead and take a look at these vectors here. So this is vector A and vector B. So what we want to do is we want to determine a potential direction for the vector A cross B, which we'll call vector C. So the notation for A cross B looks something like this. So you see this X right here. That's how you can determine that this is a cross product that we're looking at. So to determine direction, we're going to use something called the right-hand rule. So the right-hand rule pretty much states that what you're going to do is you're going to point your fingers out in the direction of A, just like this. You're going to curl your fingers so that they point in the direction of B, and then you want to stick your thumb out. And then the direction your thumb points in, that direction is the direction of your cross product. So when I just demoed the right-hand rule there, you might see that we get a cross product vector that points in this direction. And an important thing to make note of is that the cross product is perpendicular to both A and B. And you'll be able to check that through checking the dot products of both A and B with the cross product. So let's go ahead and try an example here. So let's say we're given the vector A. Let's say we're given the vector 5, -2, 3 for A. And then vector B is going to be 1, 4, -2. Let's do 1, 4. Why not? Let's do 1, 4, 0. So here's what we're going to do. We need to compute what A and B are. Or A cross B is. Sorry, I don't know why I just said that. So, A cross B can be computed using what's called a 3x3 determinant. So, we're going to be taking the determinant of a 3x3 matrix. And here's how we're going to do that. So in the first row here, we're going to put the basis vectors I hat, j hat, k hat. And these vectors right here are the unit vectors that point in the x, y, and z directions respectively. And when I say unit vectors, that's a key that means that each of these basis vectors have a magnitude of 1. So just keep that in mind. This is I, j, k. And then in the second row here, we're going to put the components of A, which are 5, -2, and 3. So it's 5, -2, 3. And then in the third row here, we're going to put the components of vector B. And taking the determinant of this matrix is going to give you the cross product. So let's go ahead and try doing that. So what you're going to do is, the first things first, we're going to sort of cross out the first column and first row. You notice that they intersect at I. So we're going to be focused on the I component here. And this is going to be I times the determinant of the 2x2 matrix that's left over. So when we cover the first row and first column, you see that we get a 2x2 determinant, or 2x2 matrix of -2, 3, 4, 0. And then the next thing we need to do is we're going to do minus j. So this is these. So this means that we're focused now on the y component, or the j, or the component of A cross B in the j direction. So what you're going to do this time is we're going to cover the second column and the first row and take a look at the 2x2 matrix that's generated, which in this case is going to be this matrix right here. 5, 3, 1, 0. It looks just like that. And then for our last piece of it, we're going to be taking a look at this k component right here, or the component in the z direction. So this is going to be the third column, first row, and you see that we have a 2x2 matrix here of 5, -2, 1, 4. And these cursive debts right here, this det, that just stands for the determinant. That means that we're taking the determinant of this matrix. So to find the determinant of a 2 by 2 matrix, we're just going to find the determinant of a matrix that looks like A, B, C, D. The way we can find that is by doing A times D, so these two values multiplied together, minus these two values multiplied together. So AD minus BC. So let's go ahead and do that for all of these values right here. So A cross B is going to be equal to I times -2 times 0, which is 0, minus 3 times 4, which is 12. So we get 0 minus 12, which is going to be -12, and this is -12i. And then let's take a look at this j term right here. So we have 5 times 0 minus 3 times 1. So 5 times 0 is 0. 3 times 1 is 3. So we have 0 minus 3, which is -3. So we have minus -3j, which can be rewritten as plus 3j. And then lastly, this k term right here. This k term, we can take a look at it. We have 5 times 4, which is 20, minus -2 times 1, which is -2. So we have 20 minus -2, which is plus 22k. And this right here, this vector that we get, is the cross product of A and B. Now what we can also do is we can check to make sure that this is the cross product, because the cross product is perpendicular to both A and B. So in other words, if we take the dot product of both of these vectors and we determine that the dot product is 0, that would mean that the vector dotted with the cross product is going to give you, is going to mean that the cross product is correct. So again, just to repeat that, because I think that was a bit unclear. When we do the dot product of either vector A or vector B with this cross product vector that we get, we should get 0. Because a dot product of 0 means that the two vectors are perpendicular to each other or orthogonal to each other. So let's go ahead and try that. So if we have A dot and then parentheses A cross B, we get 5 times -12 plus -2 times 3 plus 22 times 3, or should I say 3 times, yeah, just to make it more consistent, 3 times 22, it's the same idea, just more consistent. 3 times 22, this is going to be -66 plus 66, which gives you 0, so check that off. And then we'll do B dot A cross B, and this is going to be equal to, let's see, we got 1 times -12, so you got 1 times -12 plus 4 times 3 plus 0 times 22, we just get -12 plus 12, that's 0. So since both of these dot products are 0, that means that A dotted with the cross product and B dotted, that means that A in the cross product and B in the cross product, the cross product is both perpendicular to A and B. That is what it's saying. So that's just a basic idea of how to compute a cross product of two vectors. Now let's get into what the cross product can actually mean. So there's a big fancy theorem for this, which we're not going to get into because that theorem is very hard to prove, but it's out there, so I would definitely look into it. So the theorem is that, let's take a look at these A and B vectors again. So if we were to complete the parallelogram, or turn this into a parallelogram right here, so we have an angle right here, theta, between A and B, the area of this parallelogram is going to be equal to the magnitude of the cross product, A and B. And this can be also shown because another way to compute the magnitude of A cross B, this is going to be equal to the magnitude of A times the magnitude of B times the sine of theta, which is the angle between A and B. So, the sine of angle A and B. So if we were to take a look at this parallelogram again, we can see that B sine theta is this height right here. So the height is equal to the magnitude of B times sine of theta. So if we were to find the area of this parallelogram, it's this base right here, A, times the height H, which is going to give you AB sine theta, hence A cross B. So the area of this parallelogram is going to be A cross B. So what we can do here is, let's say we were given 4 random vertices. And what you can do with it, so what you can do with that, let's say we had vertex K, L, M, and N. What you can do with this information is you can have a parallelogram such that K, L, M, and N are the vertices of this parallelogram. And that's all you know about it. You can use the cross product to find the area of this parallelogram. And even further, if we go ahead and slice this parallelogram in 2 along its diagonal, you'll see that we get 2 triangles out of this. Let's call this triangle A and triangle B. These triangles here have equal area. So you can say that the area of this triangle is going to be equal to 1/2 of the magnitude of the cross product, because it's just 1/2 of the area of the parallelogram, which is determined by these vectors right here. And let's say we were to hypothetically have this problem. I'm not going to go ahead and work through an example because that would take too much time, but here's how you would work through it. So let's say we had these KLMN, and that was a parallelogram. What you can do is you can find the displacement vectors of KL, so you can find what KL is and find what KM is. And then if you take the cross product, of KL and KM, that would actually give you the area of this parallelogram. Because if you take a look here, it's analogous to what we have here with A and B, and that being the area of the parallelogram. So you have A equals KL cross KM. And then you divide by 2, and so we would get the area of the triangle is 1/2 KL cross KM. So that's just an example of a problem you might see with the cross product, and that's just an application that you can get out of it. So let's take another example. Let's go ahead and expand this into the 3rd dimension here. So now we're going to have 3 vectors, and we're going to have what's called a triple scalar product. That sounds like a bunch of fancy words, but just bear with me. So let's say we had a vector A, a vector B, that pointed in this direction, and a vector C. So we're going to get a 3-dimensional parallelogram, also known as a parallelepiped, which is a pretty fancy word. So we're just going to say, I can just go ahead and write that here, parallelepiped. I think I spelled that right, but it doesn't really matter if I did or not. So we can use this triple scalar product to determine the volume of this parallelepiped. So how can we do that? Well, this can be done by doing what's called a triple scalar product. So if we were to find this, if we were to find the area of one of these faces, which can be done through A cross B, and we multiply by this height right here, the magnitude, which would be the magnitude of C. Or actually, no, if we multiplied with the dot product with this C right here, this vector C, that would actually give us the volume of this parallelepiped. So what would that look like? So we would have something like C dot A cross B, and the way we can compute this triple scalar product is by taking another determinant of a 3x3 matrix. But this time, it's a little different. This is a determinant, except instead of ijk being at the top, we're going to actually have the components of C at the top. So we're going to have C1, C2, C3, and then for our second row, we're going to have A1, A2, A3, and this would be B1, B2, B3. By taking the determinant of this matrix right here, following the same procedure that we illustrated here with taking the 2x2 determinants, by following that same procedure with this matrix right here, you can find the volume of this parallelepiped. And those are just some applications of the cross product. The cross product can also be used for something called planes, which we're going to get into in the next video. But for now, this is what you'll need to know for the cross product. So that's it for